Hello students, so today is the second lecture of DNF block. So for that, today we will talk about the physical properties and the trends in the atomic size and ionic size of the D block and F block elements, right? After that, we will solve some questions related to it and we will have a brief overview for the ionization enthalpy. Okay, so let us start our today's class. Now, if I look at the physical properties of the say DNF block, you will find that all of the properties are in accordance with the properties of metal. Okay, you can see here that nearly all the transition metal display typical metallic properties, right? Which are high tensile strength, ductility, malleability, metallic luster, high thermal and electrical conductivity. Okay, so this all are what? This all are the properties of a metal, right? For that reason, the DNF block elements are considered as metal. So they're mostly metals. I would not say all of them are metals, but they are mostly metals. Now, before moving to the say our so-called DNF block elements, we will look at the metallic bonding. Okay, since they are metals, so the bonding that is involved between the atoms of the DNF block elements are metallic bonds. We will look at what a metallic bond is. Clear? Okay. So, if you just consider the uh, crystal structure of a D or F block element, you will see that the D and F block element have a sea of electron. So like a C electron, you can say a C electron model is applied onto that. So there is a sea of electrons. What happens that the energy gap between the valence shell, okay, valence band and the you can say valence bond and the conduction band. So the energy gap between these two bands are very less, and electrons move from the valence band to the conduction band. And once they move to the conduction band, they are free to move here and there, right? They are free to move here and there, and for that reason, since they are free to move here and there, they creates a sea of electrons. Now, this sea of electrons of one metal interacts with the nucleus of the other metal, and this creates an interaction. Okay, they just move from here to there, and these free electrons are responsible for the properties of a metal. So most of the properties of a metals can be explained on the basis of metallic bonding. Now, one more important thing here, that if you talk about that which electrons are more susceptible to the removal, then I would say that unpaired electrons are more susceptible. So what does it mean? It means that if a metal is having more number of unpaired electrons, it means that it will have a greater number of C electrons that are available, and hence their interaction will be greater, resulting in strong metallic bonding. Okay. Now, keeping this concept in mind, we will move to see the variation in the atomic and ionic size. Now, this explanation is very important for the case of ionization enthalpy, because there you will find that this ionization enthalpy is kind of affected by the metallic bonding. After that, some properties like melting point and boiling point, about which we'll talk in the next lecture. So those properties are kind of also influenced by the C electron model, or the we can say due to the availability of the valence electrons. Clear? Now, talking about these properties that are written here. So the properties are high tensile strength, ductility, malleability, high thermal and electrical conductivity, metallic luster. So you've seen all this, right? You've seen all this. It means that you can just bend them into wire. Okay, you can just hammer them to the sheets. They have high tensile strength, which means they don't break easily. They can conduct electricity and and plus heat. So these are all the points that are related to metals. Clear? And plus these are all shown by the D block elements, which signifies or which illustrates that these D block elements are metals. Now, talking about melting point, so as I have told you that the melting point is why is there a high melting point for the metals? Because of the presence of greater number of electron from the n minus 1 D in addition to the ns electron in interatomic metallic bonding. So same thing is written. Now, one thing is one more thing is added here. So in addition to the unpaired electron, we have one more theory that since the d orbital are present on the outer side, or they are having a greater energy, it means that they can be what? They can be moved. Okay, they can be moved easily to the conduction band. Okay, I'm not talking about the removal from the core atom to make it ionic. I'm just saying that the electron movement from the valence band to conduction band is easier. Okay, why? Because the d orbitals are not that much penetrated towards the nucleus. Is it clear? Okay. Now next, there is an exception to that, and the exception is explained by the D5 configuration. Okay, so for magnesium and technetium, there is an exception. Why is it so? Because to remove the d electron, or to move the d electron from valence band to conduction band, it should be removed. Okay, and the case of D5 configuration, it is having the highest exchange energy. Clear? Now, due to this high exchange energy, the half filled orbital are very stable. Okay, what are they? They are very stable. Now, this is the trend for that. Now you can see that there is an increase. Okay, first there is an increase, and then there is a sudden decrease. So this decrease is not that much prominent. It is due to the molybdenum and chromium, which is having D5 configuration, right? Which is having D5 configuration. And magnesium and technetium are having low melting point. Okay, they are having low melting point as compared to the previous one. For why? Because molybdenum and technetium are what? They are having a greater number of, you can say they're having a significant amount of hydrogen metallic bonding. Clear? So, talking about this, so we start from scandium, titanium, potassium, calcium, scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, and then zinc. Clear? So, potassium, calcium, scandium, titanium. So, titanium is how many electrons? It has, say, it has 2 electrons in the s orbital and 2 electrons in the d orbital. Now, the 2 electrons in the d orbital are not paired up, so they can be moved to the conduction band. Then vanadium has 3 electrons, chromium has 4 electrons, but manganese has 5 electrons. And since it has 5 electrons, so it is a stable configuration, half filled. So they cannot be removed easily or moved to the conduction band. For that reason, we see that there is a less extent of metallic bonding, and they fall in the lower region, right? Similar is the case for technetium. Okay, similar is the case for technetium. Is it clear? Okay. Now, here is a important point that you don't see a greater change when we move from iron to nickel. Iron, cobalt, nickel, there is not much prominent changes. So this trend is also important. Now talking about this series. So if you talk about this series, then of course the rhenium falls, right? The rhenium falls, but the fall of osmium is greater than the rhenium, and we don't see any you can say predicted trend. Okay, right? So this is the trend for melting point of the d block transition elements. Is it clear? Okay. And now we'll talk about the enthalpy of atomization. Since the extent of metallic bonding is very high, for that reason metals have a very high enthalpy of atomization. Okay. What do they have? They have very high enthalpy of atomization, and they tend to be noble in their reaction. Mean they are not that much reactive. Okay, as compared to transition element, the d block elements are not that much reactive. So second and third series have greater enthalpy of atomization than the corresponding elements of the first series, which account for the more frequent metal metal bonding. Now, what is the meaning of this? See, the second and third transition elements, they have their electron in the more outer shells, right, as compared to 3D. 3D, as compared to first series, the second and third series have the electrons in a more outer area. Clear? Now, what happens as a consequence of that? You will see that their electrons can be easily moved from the valence band to conduction band. Okay, again, I am repeating. that since the electron of the second and third series are present on the more periphery of the outer side, okay, you can say that they are present or more on the outer side as compared to the first series. Therefore, for that reason, I would say that it is very easy to remove electrons from their valence band and move it to the conduction band. Now, what is the result of that? It results in more and more number of electrons that are available for metal-metal bonding, because metal-metal bonding is totally dependent upon the number of electrons. More is the number of electrons that can be facilitated, more will be the metal-metal bonding. Okay, so we have seen this, that the metal-metal bonding is nothing but the sea of electrons that is resulting in that metal-metal bonding. Clear? Okay. So in general, ions of the same charge in a given series show progressive decrease in size with increasing atomic number. So as we move from in a given series, and if they have the same charge, then there is a decrease in radius within the atomic size. Okay, there is a decrease in radius with increasing atomic number. Why is it so? Because the new electrons, as we are moving across the period, the new electrons are added on the outermost shell. And due to that reason, the outermost shell will experience greater pull. Clear? Because already it is positive charge, right? Now, as we introduce electron, it will be attracted more towards, and hence the whole shell will just contract, and that will result in a smaller shell. Clear? Okay. And one more reason is that the shielding effect of the d electron is not that much effective. Means the electrons that are present within the shell do not affect or do not shield the electrons present in the same cell by that much strength, right? Now, due to that reason, you would see that they are not effective in shielding, and hence their atomic size decreases. So, in general, ions which are having the same charge, if you're moving from left to right, then their size decreases vastly. Clear? Yeah. So this is the trend here. Okay, this is the variation atomic size and ionic size. Okay, so we are talking. This is for the atomic size. So what happens here? If you see that for 3D transition elements, okay, for 3D transition element, or you can say the first series, this is the line. The green line is for the first series. For blue series is for the second. Blue line is for the second series, and red line is for the third series. Okay, clear? Now, one thing to notice here is that the difference between the corresponding atomic radii is greater for the case of first and second, but it is smaller for the case of second and third. So this trend is important. We will counter this trend, or I would rationalize this trend with the help of lengthenite contraction, which is an important part of the DNA block, in the upcoming slides. So what you have to notice here, that the difference between the atomic radii of first and second is very high as compared to the second and third difference. Is it clear? Okay. So this is the trend, right? This is the trend. Now, as we have seen that as the number of, you can say the atomic number increases, the number of electrons in the outermost shell increases, and we see a decrease in their ionic size. See, the size is decreasing from left to right. Okay. Why this is so? Because the net electrostatic attraction between the nuclear charge and the outermost electron increases, and the ionic radii decreases. Now, the same trend is observed for atomic radii, okay, of a given series. Means the trend is same for ionic and atomic radii. Clear? However, the variation within a series is quite small. An interesting point emerges when atomic size of one series are compared with those of the corresponding element in the other series. So we are talking about this thing. Okay, this difference here, this difference is huge, whereas this difference is very small. Almost they are co-linear, means they are running on each other almost. Clear? So the in curve from the first to the second of the element, the difference between the first and second increases, right? But the radii of the fifth series are virtually the same. If you look at it, first time they appear to be almost same. And this phenomena is called as lengthenoid contraction, and it is associated with the introduction of 4f orbital. So as we move from 4d to 5d, there is a feeling of, you can say, the 5f orbital are, sorry, the 4f orbital are filled first before the 5d. Okay, clear? So what I am saying is that the 4f orbital is filled first as compared to 5d. Now for that reason, what happens? We see the lengthenoid contraction. Okay, and means the size is contracting than the predicted size, and for that reason we don't see that much difference. Clear? So the same thing is mentioned here. The filling of 4f before 5d results in a regular decrease in atomic radii, and this is called as lengthenoid contraction. So this point is very important, that the intervention of 5f orbital, or the filling of 5f orbital before, sorry, 4f orbital before 5d orbital results in a regular decrease in the atomic radii due to the poor shielding of f orbital. Why is f orbital poor in shielding? So as we move, or as we increase the value of L for different orbital, what do? We diffuse the orbital more and more. So S orbital is kind of diffuse, means it is, you can say, it is spread out. Okay, spread it out. So f orbital is more spread out as compared to d. D is more spread out as compared to p, and same as for s. Okay. So f orbital is what? It is more spread out. Means the same electron, because one orbital will have two electrons, but that same electron will be present in a greater area, or it would be spread. It would spread in a greater area. Now that would result in a decrease of electron density. And electron density, if something is having a greater density, then its shielding is more. This is obvious. Okay, so if five soldiers standing in a place and they're defending their fort, and suppose there is another fort where same and the other fort is of the same dimension, and there 10 soldiers are there, right? Now due to the increase in density, that fort is more safer as compared to the previous one, which has only 5 soldiers to protect the fort. Clear? Is it clear? So what happens, that the electrons are same, number of electrons are same, but they are now present in a greater area. That means their density is less. For that reason, what will happen? Since the density is less, the nucleus will apply a greater force on the outer electron, and they will be pulled more inner. Okay, more on the inner side. Got it? What is the net result of lengthenoid contraction? Is that the second and the third series exhibit similar radii. So the same thing is written, that if you look at the graph, then you will see that virtually the 3D and the third series and the fourth series are having almost same atomic radii. Now, what is the advantage of this, or what is the result of this? So, if they are having a same radii, and if in the case there is a case that they have same number of d or electrons, then I would say that they will have similar chemical properties. Now, if they are ion, then they should be at the same charge also. Clear? Got it? Now, we have told you that due to the lengthenoid contraction, what happens? Due to poor shielding, the 5d orbitals, right? The 5d orbitals are experiencing a greater force of attraction due to the poor shielding of 4f orbital because of their diffuse shape. Now, greater force of attraction means the outer radii will come more closer, and hence their atomic radii will decrease. Clear? So for that reason, we see this trend. Okay. So this trend that is being seen here, that almost the 4D series and the 5D series are having the same atomic radii in this region, especially, is especially due to what? Is especially due to the poor shielding effect of 4f orbital. Clear? Got it? Now, next. Now, as we move, so same thing written, that as we are increasing the nuclear charge, or as we're moving from left to right in a period, then we see a decrease in the size of the entire 4f orbital. Now the decrease in metallic radii coupled with increase in atomic mass results in general increase in the density. So what it is saying that since metals are getting closer and closer, it means that there is a decrease in metallic radii, and coupled with increasing atomic mass, that would result in a higher density. Means we are trying to acquire more and more atoms in the same place, okay, or you can say the more and more mass in the same place. Therefore we are increasing the volume. Thus from titanium to copper, the significant increase in the density may be noted. Clear? So what it is said that if you move from titanium to copper, there is a significant decrease in density because of the smaller number of unpaired electrons. Now here is a question for you, that why do transition metal exhibit higher enthalpy of atomization? So we have already encountered this question. What is the answer of this question? It is very simple. Okay. What is the answer? The answer is due to the presence of metallic bonding. So I have explained it in the start only, that what is metallic bonding. Due to the presence of metallic bonding, we see a greater enthalpy of atomization for the transition metals. So here it is written that due to the presence of unpaired electron in the atom, they have a stronger interatomic interaction. Which interaction? Interatomic interaction, which is due to the sea of electrons, and stronger bonding between atom, resulting in higher enthalpy of atomization. Clear? Next question. In the series scandium to zinc, the enthalpy of atomization is the lowest. Okay, scandium to zinc, the enthalpy of atomization of zinc is the lowest. Why is it so? Just if you look at the electronic configuration of zinc, then it has an electronic configuration of 4s2 and 3d10. Okay, this is the electronic configuration of zinc. Now, due to the completely filled d orbital, its electrons are not that much available for our metallic bonding. And for that reason, we see that the enthalpy of atomization for zinc is the lowest. Clear? Okay. So here the same reason is written, that for zinc, the enthalpy of atomization is lower because it has a completely filled 3D subshell. Okay. It has a completely filled 3D subshell, and that result is stronger. Here it would be weaker, not stronger. And that results in a weaker metallic bonding, and due to greater extent, lower extent of lattice energy. The second point is wrong. Sorry for that, because it has less number of unpaired electrons, so it will have weaker metallic bonding. Okay, got it. Now, next, let us talk about ionization enthalpy. So we'll talk more about this. Now, let us just have a brief overview first of all. So, as the nuclear charge increases, the ionization enthalpy increases. So this trend is very obvious. So if you talk about the trends in d block elements, then for first transition element, this trend is not that much, you can say, patterned. Okay, the reason behind it is reorganization of electrons. So what happens, as soon as we remove an electron from a d orbital, that results in reorganization of the electron. And why is it done so? It is done so to minimize the energy, right? Why it is done? It is done to minimize the energy. Now variation across elements is much less compared to non-transition element. Why? Why this variation is less? So it is saying that if you move from left to right in the case of S block element, then you will see that the the ionization enthalpy is varying larger. Okay, but in case of d orbital, it is not varying in that much difference. Okay, and the reason is obvious. Due to the d orbital involvement, these electrons can be removed easily, right? Okay, the first ionization generally increases, but the increase is less step. Okay, so let us look at that in the next class. What does first transition series looks like? Okay, so if we talk about the second and third transition, the increase is more significant. Irregular trends in the enthalpy of first or the 3D series is seen. So we have talked about this and why it is happening, because of the relative energies, or you can say the reorganization of electrons in the d orbital. Clear? Okay. Now next, ionization enthalpy increases only slightly. Doubly or more highly charged ion have DN configuration with no 4s electron. Generally, the trend of increasing value of second ionization enthalpy is seen. Okay, so we will talk about the exceptions in the next class. Okay, so we'll see to that exception. So why is it so? Half filled are having a exception. So the reason is very obvious. Due to the presence of exchange energy, there is an increase in stability, right? And no loss of exchange energy at D6 configuration. For that, it is less stable. So if you want, you can just go through this point. The same point is mentioned that the uh, higher value of copper, nickel, and zinc indicate the difficulty in obtaining oxidation state greater than 2. Ionization enthalpy provides some guidance on the stability of the oxidation state, but the problem is complex and not easily generalized. So with this, I end my lecture. So we have completed the starting trends of the metallic bond and all. We will move to some more trends in the next class. For this class, this is good enough. Okay, thank you.